fairly simple. And if you answer a question, then you get a piece of candy.
And you don't have to be correct either.
Yeah.
So, what kind of candy? Just give you good effort. There's a bunch to
I see Twix there.
There's Twix, Reese's, Snickers, and Midnight Milky Way. So, let's go ahead and get started. Okay, this is getting into the basics. This is just a frequency wave, and basically what a balanced signal is, it's pretty self-explanatory. It's when you have as much positive voltage as negative voltage, so it's averaging out 0, as you can see. The positive and the negative ones are the same. So if there is a non-zero average, which means if like the top one was bigger than the bottom wave, then energy is wasted, and that's in the form of heat. So going over that slide, what is a balanced signal? Raise your hand. I know, right? There you go, just go for it, yep.
It's when your signal is flat to zero, so there's no higher negative or positive wave.
Exactly, candy.
I want Twix.
Twix.
If I'm going to be the guinea pig, I want Twix.
And can someone tell me in what form the energy is wasted?
Heat.
All right, here you go, candy.
Twix. She's got like 2 bags of Twix.
You guys can trade it. Okay, moving on. There is something called non-return to zero, and non-zero invert, and that's basically how the voltages are represented. So for non-return to zero, it's when a positive voltage is represented by a 1, or as you can see in this photo, it's like, raised up 1, so it's like high. And then the 0 obviously represents a lower line. And then for non-zero, non-return zero invert, it's similar, but when there's a change or like a transition, it represents that within the cell. So can someone tell me what the difference is between non-return to zero and non-return to zero invert? Go for it.
Okay, yeah, it does the transition within the cell, and not after it.
Exactly. Candy.
Okay.
So we gotta switch it up. We can't give you all Twix.
Okay.
You guys can just shout out the answers. Okay, on to baseband and passband transmissions. The difference between those is that baseband, it sends the signal as it is without modulation. So basically, it's sending the signal baseband, right? Makes sense. And for passband, it shifts the signal to be transmitted within a higher frequency, and then once the signal is received, it goes back to its original state. So, can someone tell me what the difference is between baseband and passband? Whoever goes first, just shout it out.
And you guys don't like candy.
You bought the wrong candy.
You don't want Twix? Or Snickers?
Okay, one's with modulation, one's without.
There you go, there it is. So, which one is basic? Shout it out.
Baseband.
Okay.
Oh, wow.
And passband, it changes from the original frequency to a higher frequency. Okay, there you go. Moving on, so multiplexing. There are 5 different types of multiplexing, but generally what it is when multiple signals are being sent, but it's not compacted, but it's grouped together in one single complex signal, and once it's received, it is separated out from those signals. A way that you can think about that is like when you're trying to send a whole bunch of files, you can either put it in a folder, or you can put it in a zip file and then send it over, and then once the person receives that zip file, it unzips it and you get all the different files that were within that. So that's one way to think of it. So, multiple signals, they are sent in the form of what kind of signal? Shout it out. One single complex signal, right.
Yay.
There you go. And what is multiplexing similar to?
Zipping.
Zipping files, all right. Throw some candy on there.
Who wants candy? Yeah.
Like, who wants candy?
Don't be shy, guys. It's okay. Okay, so as I said, there's 5 different types of multiplexing. Can anybody name one of them?
They're all right there.
Anybody name one? One type of multiplex.
It's meant for y'all to get candy. That's our point.
Time division.
Time division. Okay, can you name one more?
Code division.
Okay.
Frequency division.
There you go. Okay, can you guys name two more? Looking for some pretty specific ones here.
Orthogonal frequency division.
All right, and there's one more.
Statistical time division.
There it is. Okay. So let's go over these two real quick. Frequency division multiplexing is when the spectrum is divided into frequency bands, each user having exclusive possession of the same band in which they're setting their signal. So an example of this is AM radio. I don't know what the difference is between FM, but AM is an example of frequency
AM is
division.
longer distance. FM is shorter distance.
Can you say that again?
AM is
Longer distance?
Yeah, the use
Yeah,
of the
what- what's
signaling
that?
FM is a shorter distance, but it's clear. The AM used to be used by the military.
There you go. You should just join this group. You've got it.
No, she's a member of our group.
All right. So and the allocated spectrum is about 1 megahertz. Yes. And then another type of multiplexing is orthogonal frequency division multiplexing, which is like a sort of subsection of frequency division multiplexing. And that's just when the bandwidth is divided into multiple sections and they're tightly packed together and they send data that way. So, can someone tell me what radio broadcasts FDM?
AM.
AM. Who said AM back there? Get some candy. I heard you. I saw it.
I don't want the candy.
Toss him the candy. Just throw it at him.
Okay.
Don't hit the thing.
Make it ring with candy.
Oh shit.
Okay.
I'm not gonna do it. Someone's asking.
And can someone tell? Yeah.
What does the AM stand for? You know?
That's a great question.
Shouldn't you know?
Well, I know that it's an example of FDM.
All right.
Ah, there you go. Also, can somebody tell me what is the allocated spectrum for FDM? About
1 megahertz.
1 megahertz.
Amplitude modulation.
There you go. AM stands for amplitude modulation. You deserve a chocolate. Give him a chocolate.
And frequency division.
Snickers? Because I'm out.
Okay.
Alright, I'll just try to get it over.
This is why we work with computers.
Okay, and can someone tell me what is one subsection of frequency division multiplexing? Starts with an O.
Orthogonal frequency multiplexing.
There you go. Orthogonal frequency division multiplexing. And now let's hear about some more.
Yes.
Different background.
Yeah, this one's mine.
Alright, so for my sections I had time division multiplexing and I had code division multiplexing. Time division multiplexing is used widely as part of the telephone and cellular networks. It's an alternative to FDM, and users take turns in a round robin type fashion, and each one periodically getting more bandwidth, or each one getting bandwidth in small bursts. Kind of shows it in that picture. And for TDM to work, the streams must be synchronized in time, hence the reason it's time division multiplexing. And also it kind of shows in this picture there's little guard times in between, and that's added to accommodate the small time variations. Or should I ask a question? What is guard time?
It's added to accommodate time variation.
Nice.
What's your question?
What is round robin used for today? Is there anything that's used for?
I think it's just a term it's used to describe what's going on. Like, I don't really think it's anything like specific like that. I think just the way the book uses it, it's just used to describe like how it turns, and it keeps repeating it in the pattern of 2, 1, 3, 2, 1, 3.
You could do the same thing with, say, like DNS, for example. If you have multiple DNS servers, it does a round robin to distribute load and stuff like that.
Oh, it's just like a good term. All right, code division multiplexing. It's a form of spread spectrum communication where narrowband signals is spread out over a wider frequency band. The benefits is that it's tolerant of interference and allows multiple signals of different users to share the same frequency. It's like the key part right there. Another name for CDM is what it uses in the book. It's code division multiple access, and that kind of goes over. It allows multiple signals to come from different users, and they share the same frequency band. There's an analogy that I'd like to use that I also got from the book, and it's that it uses an airport lounge, and basically it says TDM is comparable to pairs of people in a room taking turns speaking, and then code division multiplexing is comparable to each pair of people talking at once, but in a different language. French-speaking couples hone in to the French and rejecting everything that isn't French noise. The key to CDMA is to extract the desired signal while rejecting the rest. So what's the key to CDMA?
Speak up.
I think I heard that.
Alright, I'll get my throwing in. There we go.
No, you did good at it. Yeah,
Alright. There are chips. There are chips that are used in it, and each bit time is subdivided into m short amount of intervals called chips, and there typically are 64 to 128 chips per bit. Each station is assigned a unique m-bit code called a chip sequence. So how many chips are per bit? I just said this on the slide, but does anybody remember?
128.
There you go. Got it. What do you want? Reese's? Twix. I like Twix. Twix is my favorite. Alright, that was short. My bad.
now you have 1 to 2.
Alright, here's an example. So for this sequence on the left here, there's it'll express a 0 bit, and while the one on the right it's the opposite. See, there's 8 bits in that one chip, and they're different. One's the opposites actually. So, all right. 1 second. Okay, so the M represents the amount of chips in the bit. So no other patterns are permitted, and CDMA uses 1 megahertz. So chip rate is 100 chips per bit, which has a bit rate of 100 or 10 kbps across the channel. So what is the chip rate per bit?
110 kilobits per second.
Well, the chip rate is 100 chips.
No, Snickers.
It's okay.
Oh, can I have Snickers instead?
Oh gosh.
Just
Yeah,
one.
like you can take that.
I can't.
All right, the symbol S is used to indicate the end chip vector for the station S. We generate the orthogonal chip sequence using a well-known method called Walsh codes, and that's an example of it right there in that picture. All the chip sequences are pairwise orthogonal, which means that the product of any 2 distinct chip sequences, S and T, is equal to 0. So that expression right there just shows that's equal to 0. Let's skip this one. All right. All right. In the first, in the A, whatever letter, It shows the chip sequences for 4 stations, just like as I showed in the example before. And in B, it shows the signal sequence and what they represent. Like the lower lines represent negatives, and the lines that are going up represent positives. In C, there's 6 examples of transmissions, and the sum, they're actually sums of bit transmissions, so you get the sum of their bipolar chip sequences. And for D, there were the recovery station signals, and to receive the signal, you must know the station's chip sequence in advance. So I'll just repeat that. So what do you need in order to recover the station C signal?
You need to know the chip sequence in advance.
Right. Alright, but that is it.
Hello, everyone. So it seems like no one wants to answer questions, so I'm not going to ask any questions. But,
Yeah, you can keep all your candy.
yeah, or we're going to take it all. So, but what my section is about is public switch telephone network, PSTN for short. Basically, what it is, the purpose of the public switch telephone network is to transmit human voice from one place to another. It's an interconnected telephone system where all the calls are made over copper wires via analog signals. And it's also known as the plain old telephone system, or POTS for short. Next here, we're going to talk about the structure of the telephone system. It was created soon after Alexander Graham Bell patented the telephone in 1876. Because of their enormous demand for the product, it created an issue where phones were, basically what happened is the phones were sold in pairs, and the only way you could connect to the phones were you had to directly connect the wires from one end to another. And it caused a situation kind of like that first object where all the wires were like, it's called a, mesh topology network, where it's all just meshed in together, and that caused a lot of issues because it wasn't really practical. It wasn't until 1878 where Bell Telephone Company introduced the first switching office, which helped to resolve the issue. And what happened then was it led to the star topology, which is like this one right here. And the middle dot represents the switch office, where all the lines come into the switch office, and they'll switch it to the other end, the correct end. That also led to more issues, and as it grew, the popularity of telephone grew. It began connecting switch offices, and that's how we get this diagram right here, where switch offices were connected to each other. The switch offices are represented by the squares. And this diagram right here basically shows how the switches work. If you were to call from the local call, you would use the local loop, which is just basically copper wires coming to the in office, which is the local office, and you wouldn't see the rest, it would be a regular telephone on the other end. But if you're trying to make a long distance call, it will have to go through all these switches to get to the other side. And next up, we're going to be talking about the politics of the telephone. And for years, the telephone company system was ruled by the Bell system. It provided telecommunication services for both local and long distance for the majority of the U.S. up until 1984. That's when the government stepped in and classified it as a monopoly and broke it up, forced to break it up, and it forced them to have this what they call a modified final judgment. Basically, it broke the Bell company up into many different little independent phone companies themselves, and they regulated their own services.
If you had final judgment, it could be modified.
I wasn't the one who made that up, but it was in the book. And so this is a diagram showing how it was basically broken up into. They were broken up into what was called 164 local access transport ladders, and within each ladder, it had its own local exchange carrier, basically independent telephone companies, as you can see represented in these little diagrams. And each of those local exchange carrier had its own PSTN, which are public switch telephone networks. Next up, we're going to talk about the local loop, which is what I stated earlier, just the regular copper wire network that they used in the beginning to connect all the telephones together, from the switch offices to the other telephones. And as we know, it's been carrying analog information well over 100 years now, and it will continue. And only because it's very expensive to replace them, as you can see from this next diagram. You can only imagine how much copper wire is going through. Just to give you an idea, it's stated that if you were to stretch the wires from Earth to the moon and back, it would go about 1,000 times. So it's impractical to just try to replace them. So what that forced the providers to do is to make use of what best they can of the copper wires. So of course they devoted much effort to squeezing as much data from the network as from these copper wires that already exist, and the new technologies such as modem and ADSL were created. But with these new technology, it kind of they have to deal with the limitations of the old local loop, like distortions of signals, narrow bandwidth, and electrical noises. All right, so let's go back. These are modems, okay? So modems are, modem use the local loop to send digital data between computers by converting the digital bits into analog. And there are many types of modem. You have cable modem, you have your phone modem, so on and so forth. And then of course ADSL was created to help transmit the data faster. Basically what ADSL stands for is asymmetric digital subscriber line. It also uses the telephone lines to transmit digital data. It's a distance sensitive technology, meaning as the connection length increases, then the signal quality goes down, as illustrated here by the diagram. And next we have fiber optics. with the limitations of the copper and of the local loops, telephone companies began upgrading to fiber optic cables. This resulted to what you see here. They labeled it fiber to the home, FTTH for short. It was much faster. It can provide up to 2.4 gigabytes per second downstream and up to 1.2 to 2.4 gigabytes per second upstream. Next thing is the circuit switching versus packet switching. There are two parts to the telephone system. You have the outside plant, which we just talked about, the wiring and whatnot, and then you have the inside, which we're going to be discussing right now, is the switching and the switch office. And the picture you saw earlier, which here, you can see what they're doing is basically they're just switching the calls to the right users. Alan D. Stroger, I believe that's how you say Stroger, was the first to invent the automatic telephone switching, which eliminated manual switching, which we saw earlier. And this diagram just shows you how it looked like. That's basically what it is, and you can imagine like a lot of those together in one room. And this diagram right here shows how a connection would be made from one end to another. The alternative to circuit switching is packet switching, which is with this technology, the packets are sent as soon as they're available through, and let me see, and it's digital signal. So with this technology, there is a delay. And as it's illustrated up there, the packets are sent. If you can imagine, like these are broken up of one signal, but as soon as it's available, it's sent one by one to the next user, whoever is requesting it.
What's funny about this picture? It's like we start off with cell phones that look like bricks, and then we got smaller, and then we went to cell phones that look like bricks again.
Yeah, but they're like paper thin though.
Yeah, but
These are more like stepping stones.
I like how we got smaller.
Yeah.
Then we had to get bigger again because we're gluttonous people.
Exactly.
So we wanted them small so they could fit in our pockets, and now we can't do that.
Yeah, but some of those are flip phones. That means they're a lot bigger than they are.
They still fit in my pocket.
See, that is true.
Hey, I had that one.
This doesn't fit in my pocket anymore.
Yeah, I had that one.
Okay, we're going to talk about mobile telephone system. And